Hey everyone, this week we've got a rebroadcast episode for you guys from our first year of doing the podcast, which doesn't actually feel like that long ago, but I guess it kind of was, about the question, the classic question that we've all asked, all wondered, why is the sky blue? Now this explanation and this chemistry lesson dovetails really well with the recent rebroadcast episode we did about bleach and the recent episode we did about dyeing blue jeans, because all these episodes have to do with color and light and all that stuff. So if you haven't listened to it or you haven't listened to it in a while, then check it out and enjoy. And we will be back next week with a brand new chemistry lesson, brand new episode. See you guys then.
Hey, I'm Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Jam, how are you doing today?
I'm good. How about you?
I'm doing good. I'm excited for what we're going to talk about today. I've been planning it for a few weeks.
Me too. I'm excited too. I don't know what it is though. And so I'm also a little bit cautious.
Well, it's about the sky.
Okay.
What color was the sky when you walked in today? Did you notice it?
I'm guessing it was blue because it was like a clear day.
Mm-hmm.
But I did not notice it. No.
Well, today we're going to talk about why the sky is blue. It is blue today. I noticed it, but only because I knew we were talking about this. We're going to talk about why the sky is blue.
Okay.
But also we're going to talk about why sometimes during the day it isn't blue.
Ah.
Sunrise and sunset, maybe.
Yeah, interesting. That is weird. It's not
Always blue.
I like that we're talking about this because it is like the classic question that people ask. Like, why is the sky blue?
Yeah, I have a cute
Like,
story
Mom,
about
Dad,
that for
why?
you.
Yeah.
About a professor teaching his daughter why the sky is blue, but taught her the real reason.
Oh, really?
Yeah, it's cute, but we're going to save it.
Okay.
Okay, so we've talked a lot about light and waves.
Yes.
So the very short answer, the very easy answer for why the sky is blue
Okay.
is that the blue light is more efficient in traveling, so we can see it more.
Okay.
The sun's light is white, and so it's made up of all the colors of the rainbow.
Mm-hmm.
We've seen that. You can separate it out into all its colors like in a rainbow. And you can do other things with the light, like scatter it.
Uh-huh.
And when it's scattered, the blue light goes the most efficient. And that's the basic boiled down answer of why the sky is blue, is because the blue light is the most efficient.
So it's not that something is blue necessarily, but that blue light just travels better so we see it.
Mm-hmm.
It doesn't have much to do with our eyes. It's more like the light itself. So the wavelength, the frequency of blue light.
There's a teensy bit about your eyes, but we'll dig into it.
Okay. That's weird.
Yeah.
So the sky is white. Supposed to be.
I don't think so. Well, supposed to be is a big word, but let's talk about why blue light travels the way it does.
Okay. I also don't know what to ask. I feel like there's ways in which this question's so simple. Not that the answer is simple, but the question is so old and simple and common and kind of funny. Like it's one of the classic, kid asks parent can't answer, or
Right.
it's like, it just is, okay? Like that kind of thing. But here we are helping parents around the world know what to tell their children. And depending on the child, they probably will not understand or it won't be satisfied. They'll have more questions.
Oh,
They'll be
I'm
like,
sure.
okay, so wavelength. Mom, what is wavelength and why?
Okay, so I'll dig in more. Maybe you can ask some questions as we go.
Okay.
So, yeah, sunlight made up of all the colors of the rainbow. When it encounters something new, like what we talked about with the rainbows, like a raindrop, the object that it is encountering does impact the way the light travels. If it goes through a prism, it breaks up the light. It changes the speed.
Right.
So the same goes for when sunlight enters into the Earth's atmosphere.
Okay.
So the Earth is surrounded by all this like baby.
All these like little baby clouds. I don't know.
Basically like a blanket of air was what I was going to say.
Baby air.
So basically a blanket of air molecules that are kept in our atmosphere.
Uh-huh.
And when light enters that, it encounters the particles, dust, molecules, atoms, all the things that are floating around in our atmosphere. And so when that happens and it encounters the atmosphere, the light will be scattered.
Okay.
So when the light is scattered, the acceleration changes. And the amount that it accelerates depends on the frequency.
Of the wave.
Of the light, yes, of the light wave.
Okay.
So blue has a much higher frequency than red waves, just in the nature of them. And frequency, you can think of it as those little wiggles. It's literally how often it occurs. It's the frequency. Okay. So the more up and down wiggles, the more often the wave occurs, the higher frequency.
How fast the snake slithers, like from the Rainbows episode.
Exactly. So the higher the frequency, the more it accelerates when it's scattered.
Okay.
So red light, lower frequency, doesn't scatter as much. Blue light has higher frequency than any light except for violet, so it scatters more than anything else.
Got it. When it is, what word did you say again? When it
encounters
something. Okay.
It's just scattered.
Okay. So just anything, whether something like a prism, it can go actually through it, kind of, or just a tree or something. Something that it encounters, or does it have to be like a...
I think for scattering, I'm not super clear on a lot of this because it gets into physics and wave and math where I'm not great. But I think your options are light can either pass through something and that could change the speed at which it travels, and that's called refraction. It can bounce back, which is reflection. It can be scattered. I don't know if it can be anything else.
Okay.
I think
but in any of those situations, blue can behave differently than red.
Which is why you see the rainbow, the colors spread out. Blue and red are behaving differently. I think in reflection, it might not change the speed, but I'm not positive. I don't know. But I can definitely say when it's scattered, it does. So the name for this kind of scattering is called Rayleigh scattering.
Rayleigh, like a person's name?
It is named after a person, a physicist, Lord Rayleigh.
Whoa.
Rayleigh.
Was he a lord, or was that his name?
I believe he was a lord.
Okay. It'd be kind of cool if his first name was Lord.
I think
people would like...
That is not his first name.
Over history, they'd be like, wow, that guy was like... and responsibilities and stuff, or whatever that lords do in England.
So should you name your child Lord? Lord Robinson?
Yes, I could.
Maybe you should.
It does sound a little bit like, yikes.
So
those people take themselves very seriously.
So Rayleigh scattering is the name of the phenomenon. It's basically when wave encounters particles that are smaller than it. Light waves encounter particles that are smaller than it.
Okay.
So you can just think of the light being scattered with the acceleration increasing when it's scattered.
Okay.
And that happens more effectively for blue light than the shorter wavelengths. So you might notice when you look further away from the sun, it looks more blue. That's because most of the other colors of light have not reached that far. It hasn't scattered as effectively.
You know what I kind of always thought it was?
What?
Well, I did always think like, okay, there's a lot of just stuff between us and the sun and space and whatever else. You can, on many days in a metropolitan area, look out. When you can see far, you can notice a haze to things because of humans and cars and whatever. But it could also just be weather or whatever it is. But it's like whenever you look further, what might not seem like much if you just had your hand in front of your face. If you then are looking like 3 miles away.
Mm-hmm.
And there's just like a little bit of particles in the air, but you're seeing through like 3 miles worth of it. It'll start to get denser and denser in terms of having an actual ability to affect what you're seeing.
So basically you thought like, if I look at my hand, there's a little bit of light, but it's not enough to block it. But if it's really far away, there's so much molecules blocking it. That's why it's kind of a light blue or something.
Mm-hmm. Well, and the blue part I thought was simply because I guess maybe I always thought that it was just the color of space, which is black, being filtered through stuff that kind of made it look a little bit blue. But it's just getting lighter and lighter the more stuff is between me and it.
Like outer space.
Outer space.
Wow.
Because sometimes if you look straight up during the day, it's the least bright blue.
Mm-hmm.
Whereas if you look all around the horizon, it's like really light blue, maybe blue. It gets darker and darker the closer up you look. That makes sense.
I don't know.
It would actually, because like you're looking through more stuff, looking to the left or right.
Interesting.
That's what I always thought. It's just like the kind of stuff that I just like make up, kind of assume like, that's kind of maybe makes sense.
Yeah.
I'll move on.
Okay, listeners. So tell us why you thought the sky was blue. Either tag us in your Instagram stories, post it on Twitter and tag us, comment on our stuff. Tell us why you thought the sky was blue and we'll repost it. I think that'll be fun.
It'd be really fun. It definitely made me feel a lot better about my own theory. Not feeling so I don't know, jerry-rigged together.
I thought it was a pretty good one. There is space on the outside of our atmosphere, so it does make sense.
And there is junk in the air. Even the stuff that we don't put there. It's like, okay, there's nitrogen, there's oxygen, there's all these things. I'm like, I don't know what color those would make space.
If they're super concentrated, yeah. I think that does make sense. So I'm surprised you didn't ask the question, which is, if blue light has a higher frequency than all the light except violet.
Why is the sky not violet?
Yes.
That I don't know why I didn't ask it.
Here's why. 2 reasons.
Okay.
Simply less violet enters the Earth's atmosphere because there's less violet and white light.
Okay.
And 2, our eyes are slightly more sensitive to blue light than violet light.
That's interesting.
So our eyes do play into it.
Yeah.
But perhaps if there's equal amounts of blue and violet and our eyes were equally sensitive, we would have a violet sky.
Right. That's kind of what I was getting at about like the sky isn't blue, it just looks blue. Like I really get interested in that, where it's like, what things can we point to and say, this is only this way because our instruments think it is. And that's the readings we're getting. But we're smart enough and we know enough about science to have figured out that our eyes or our ears or our nose or whatever it is we're talking about are not perfect.
Yeah.
So our brains have been able to figure out that our bodies are wrong. And that's interesting to me, to be like, this guy's not blue. We just all think it is.
It's perceived to be blue as a result of Rayleigh scattering.
Yeah. All of us that can walk and talk and suppose and speculate about why things are the way they are think that it's blue because we're all imperfect equally. But it's not.
I mean, kind of it's not. I'm of the opposite camp where I think it looks blue, so it's blue. It feels cold, so it's cold, which is almost like embracing the subjectivity of life. But
yeah,
that's a little philosophical for this show.
That is.
So.
I think it's just, I like the idea of like, what if we could stop being human just for a second and look around the world and what things...
As perfect robots.
Yeah, as perfect somethings, whatever it is.
Perfect objective observers.
Yeah, beings, whatever they are. And what would be different would be so fascinating. One would probably be like seeing all the waves we don't see because we only see a certain fixed amount.
You'd see ultraviolet.
Yeah, we see ultraviolet. All these things that...
You'd see radio.
That to us seem to make up our universe and our world, daily life. Would seem like such a small sliver of all the things.
Interesting. That's interesting and overwhelming because it would be hard to see that much stuff, I think.
Yeah.
And what even is the definition of the perfect objective observer? What are they looking at?
Right. That's why it works philosophically, but it doesn't work
in real life.
In real life.
Mm-hmm.
It's like you can just pretend that one exists and then just talk about what if we were it. But yeah, you can't get anywhere. So I guess that's why philosophy is not science. And
why I got a B in philosophy, because
nice.
I felt that this was not super interesting. I felt this conversation was just not that class. Okay, so I'm just not good at those big theory questions. You know, those are I have a hard time sitting and holding on to things that I don't understand.
Right.
Like this is just all in theory. What's the point? So,
yeah.
Okay. Let's get back.
That's why it's not violet. That's why I don't see violet in the sky. There's less violet around and our eyes are less sensitive to it.
Exactly.
Okay.
Now, why is the sun orange or red when it sets, do you think? Or does it look orange or red when it sets?
I mean, the first thing I think a lot of us would say is like, well, it's on fire.
It's definitely on fire.
So that's one thing. I mean, how much does it have to do with the fact that it's like such an extreme angle? Because obviously there's another part of the world where every time the sun's setting somewhere, it's super not setting there.
Yes.
Somewhere else. And it's just a normal yellow day there. So is that part of it?
That's absolutely part of it. So when you're looking off at a random point in the sky, when the sky is blue, you're seeing the light that's been scattered away from the sun's light. You're not looking at the direct path of the light. You're seeing the light that's been scattered away. But when the sun sets, you're more in line with the actual light that's coming from the sun. So instead of seeing the light that's been scattered away, you're left only to look at the light that has not been scattered away. And the light that is least efficiently scattered are the reds, oranges, and yellows.
Got it. So they're getting caught somehow, not scattered.
They're just still in the line of sight.
They're still in the line of sight.
So if you're looking
blue, because it doesn't take much, and blue is like, pew.
Right. It's just gone. It's been scattered away.
Got it.
So if the sun was setting not through an atmosphere, theoretically, it would just look the same white light that you see when you look up at it. But because it's setting through an atmosphere, you're looking directly at the sun because of the angle it's at, as opposed to when it's up in the sky above you. You're looking directly at the sun. Blue light has been scattered away, and what makes it through are these warm red colors.
And we're kind of helped by, either clouds or objects or whatever. As it gets lower and lower, you can obviously get to where you can actually look at it and not like hurt your eyes. You can't quite look exactly at it until it's already gone or something, but it's helping that you can actually then see its direct path of light because it's kind of being filtered more and more.
Right. So it's not just that you're more in line with the sight, but because of the angle it's at, it's passing through more of the Earth's atmosphere. So more of the blue light is scattered away, leaving the less efficiently scattered light to reach our eyes. So it's almost more filtered by more of the atmosphere, and we're in the right angle to really see that.
Right. Yes. Okay, that makes sense. And that kind of, not that I had that sophisticated of a thought to it, but it kind of aligns with my non-scientific theory about stuff in the air. And by stuff, I didn't even mean like pollution necessarily. There is obviously part of that, but like just all the elements, all the stuff.
Well, and actually pollution does have an impact. It can change the color of the sky because those little particles from aerosols and all the pollution are small enough to take part in Rayleigh scattering.
Okay.
So they can actually play a role in changing the color of the sky because they are helping scatter the light.
Interesting.
So they can amplify the sunset because they're scattering more of the blue light away. They can do that. I've read some articles that have talked about that. Absolutely.
when I was in Zimbabwe a couple years ago, this probably happens other places too, but this is where I observed it. There can be a lot of dust in the air, either kicked up from animals or whatever. So much land that is not being used by stuff, or a lot of roads that are dust roads. And so there was a time where it was like we were driving somewhere and the sun was still kind of high. I mean, it was definitely afternoon. Let's just say 4 p.m.
Okay.
Normally you would not be able to look directly at the sun at 4 p.m. And there was enough dust in the air. I couldn't even really like taste it. It wasn't like there were just clouds of dust everywhere, but I could look directly at the sun and just look this red orb, kind of like a Star Wars sort of deal.
Oh, interesting.
It was so weird. I have a video of it I could show you. It was just so weird.
So it may be that the dust in the air was scattering the blue light away more efficiently, and that's why it was looking kind of red orangey.
Yeah, looking red orangey, and then enough, maybe just light in general was being scattered and filtered and whatever else so that I could still look at it. Like not only was I seeing red, but also its intensity was
diminished. Probably because there's more of a physical barrier.
Yeah.
So that's it. That's why the sky is sometimes blue and why the sky is sometimes not.
Interesting.
It's all about Rayleigh scattering. And if you tell me this answer back, I'll tell you the cute story of my professor's daughter.
Okay. When you say this answer back, do you mean like explain it back?
Oh, yeah. Yeah, by answer back, I definitely mean when you explain it back to me.
Okay. Yeah.
I haven't slept much, so my language is scattering.
Really scattering. So light, we have talked about a lot. Most of the light we deal with out in the day time, and even light in rooms and stuff, is white, which means it's made up of all the colors. So, but they do have differences, not just in color, but in wavelength. And so if something causes them to be messed with, broken apart, scattered, refracted, or whatever, then they will behave in those different ways. Not like, not crazy different, not like different elements on the periodic table, but their differences will have an effect, like the rainbow. So the light coming from the sun is white, but whenever it strikes our atmosphere and is coming through a lot of atmosphere to get to our eyeballs, it's going through a lot of things like gases, whatever makes up our atmosphere, I guess. Things that can scatter these rays of light. And so the blue light, which has compared to other lights we're used to seeing in the sky sometimes, like reds and oranges, blue has a much faster wiggle, much faster wavelength.
Wiggle.
And so when it's striking those things, it could cause it to scatter. It scatters really easily and quickly. Like, it's like, pew, pew.
Right.
And just like gets out of the way while it's hitting things. And red and orange and other light that has a lower frequency, they're like slithers, are slower. They don't do as many.
Right.
And so
just for visual aid, Jam for red and orange is moving his hand up and down like a wave that's going slow. And then for blue, he's wiggling his hand up and down really fast.
Yeah. Yep. Something that has to be seen to be believed. And those slower frequency types of light don't, man, this is kind of hard to put words to. I feel like I don't know why. I know exactly what I'm trying to get at. They don't like scatter in the same way that blue does. Blue's like totally fine. They like ricochet like a bullet. And so when we look in the sky, we're seeing tons of blue. Right. The blue is fine. It hit the stuff. It ricocheted. It's all over. The red and the orange did not somehow.
It did. So you're close.
Okay.
So that's a good explanation.
Do we still get to hear the cool thing?
Absolutely.
Okay.
So the only difference is they both get scattered.
Okay.
But when they scatter, the acceleration increases.
And then blue hits our eyeball and gets places.
Mm-hmm.
And we're not seeing red and orange.
Right. And how much it accelerates is directly related to the frequency. And so actually, because of the difference in frequencies between blue light and red light, blue light is actually scattered 10 times more efficiently.
Wow.
It increases about 10 times more in acceleration than red light does.
So all this blue light's like going everywhere very fast, so much faster.
Right.
New blue light is coming and lapping this slow orange red light.
Maybe if it was traveling on a track path at a high school, like you've got your your photons are like little tiny circles and they're driving on a track. And then a photon hits a particle that makes it scatter and breaks into all the colors of the rainbow. The blue light is going so much faster than the red light. That's a fun example. I enjoy imagining a photon now as a white little ball running with legs running on a track. And then it hits a particle that makes it break into all the colors of the rainbow. And then you can see on the track that the violet is running, I think, even faster.
Yeah.
Then blue is 10 times faster than red. And then green comes behind blue. And so that you can see the change in acceleration.
So you have like 6 or 7 lanes like you have on a track. And each one is a color. And it's like they could be that much different. So it might be like red and orange are not that far from each other.
Right.
But then blue's like way up there and violet's like already on the next lap. That's crazy.
That was a good visualization you put in my brain. Good job.
Hey, anything I can do to bring things into non-science language for a second that might either be a really ridiculous analogy or end up bringing about a good one.
I kind of want to make a little video of that, of photons. If anyone's a cartoonist and can do that, I would be so happy. It'd be so cute.
Cartoonist or like digital animator kind of person.
Right. Yeah, that would be adorable. That would be the cutest science video. Okay, so that's all I have for you. And you got it right. So I'm going to tell you the little story.
Okay, I'm ready.
So one of my professors, he's an analytical chemistry professor, and his daughter asked him why the sky is blue. And he taught her the chemical formula. I guess chemical formula is not right. The mathematical equation for why the sky is blue behind Rayleigh scattering. So the equation for frequency is C over lambda. So the increase in acceleration is 1 over lambda to the 4th. So if anyone asked this little girl why the sky was blue, she would say 1 over lambda to the 4th.
Oh gosh.
Isn't that so cute?
It's cute, but it's also like I kind of put myself in the classmates' like shoes where like there's this girl whose dad's smarter than everybody else and she's saying that stuff. She doesn't even understand it really. But she, whatever, that. It's just like, those are the.
I think it's cute.
I mean, if it was my little girl, that would be the cutest thing ever. But I just remember being around kids like that. And it was like, okay, all right. Yeah, that's why we don't ask you questions. That's why you're not coming to my birthday party.
Well, I think she probably was just fine on birthday parties, but I thought that was a fun, cute story. So,
that is cute, and especially that she remembered it.
Yeah. So you can tell your friends 1 over lambda to the 4th if anyone asks you guys why the sky is blue, listeners at home, or you can tell them the real answer because now you know both. Now that you heard that fun, cute story, what was something good that happened in your week?
So I think like several Q&Rs ago, a friend and listener of ours asked like an update on my employment situation.
Yes.
And I said, yeah, I'm still freelancing. So that's been like not a lot of stuff. There's been a consistent amount, but that consistent amount has been not very much.
Right.
But it's not been 0. So that's been interesting.
Right.
But over the past 2 weeks, it's like ramped up a lot. And I've had like consistently 4 clients that I'm doing stuff for.
Nice.
And that's been really cool. It's been tiring. It's kind of like imagine just starting like 3 part-time jobs in 1 week.
Mm-hmm.
So it's not like no one would pick to do it that way.
Right.
It would spread them out a little bit, I think. But it's been really cool. I've enjoyed that. My schedule's gotten crazy suddenly. I'm trying to get a handle on it. But it's not like I'm working 80 hours a week. It's just that having 4 different jobs, it's like just juggling 4 different objects.
Yeah.
It's chaotic, but I think I'll figure it out. So that's been good. It's been tiring, but good. Definitely thankful to be having more work, and I'm excited by a good amount of it to where it's fun to help people figure their stuff out, help them get to a better spot in whatever it is they're trying to accomplish. A good amount of it's marketing stuff, which I love. So that's been really, really enjoyable. Yeah.
Yeah, I've had more of a front row seat to you kind of picking some of those things up. So I think it's been fun to watch that develop. And
so it's old news.
Not old news.
Just kidding.
But news that I was present for the making of.
Yeah.
I am really excited for you to have your new jobs and to be getting stuff in place. But, my goal is for you to be my full-time co-host and producer.
Yeah. So until that day comes, I just need to have some stuff to do.
Right.
Just to
not
be
keep
so
you
bored.
busy.
Yeah. Because oh my gosh.
I don't want you to be bored. Yeah.
Yeah.
Well, congratulations. That is really exciting. It was I got some of those updates as they came, and it was kind of crazy balancing everything for you, I know, but
yeah, we had to switch up some recording stuff and stuff like that, but
I think it'll be good.
Yeah, me too.
Yay.
I'm pumped about it.
That's exciting.
So that's been me. What about you?
Well, actually, I'm gonna do 2 in 1 because I'm a cheater.
Oh my gosh. I love how you waited to say that. I could have done 2 in 1, but you didn't say that before.
Well, you had 3 jobs, so it's kind of like you did 3 in 1.
That's true, but I didn't describe each of them. And it'd be kind of weird to be like, so one of them's this guy, and I'm helping him do this, and another one's this guy, and he lives at...
Well, mine is 2 in 1 that are related.
Okay.
So I had a qualifying exam this week, and I mean, they're not super important, but basically when you finish your classes and you're getting your PhD, you have to pass these qualifying exams at most institutions, which basically just demonstrate that you have mastered the material and you are ready to be what's called a candidate. Mm-hmm. A candidate only has to finish their research and write a dissertation to be finished. Mm-hmm. So the qualifying exams are a big deal. Mm-hmm. And I passed them for organic chemistry, and then I switched gears, so I have to take a few more. And it always feels really good when you finish one. Mm-hmm. So that's a really exciting feeling. And I took my first one for education today, so very exciting.
Yeah.
But the thing that happened this week, leading up to my qualifying exam, I was on Twitter a lot less. And there was this really cool Royal Chemical Society did a poster presentation on Twitter. So you basically did a virtual conference on Twitter. And I love Twitter.
I think I saw this and meant to ask you about this. So it's kind of like you're answering a question I forgot to ask you.
That you never asked. Okay, yeah. So, well, I love Twitter, and I was so sad that I missed it. I got on at like midnight and realized what had happened. I was heartbroken. So I tweeted that I was sad that I missed it. And to check out Chemistry for Your Life. That's probably what I would have done a poster on anyway. And there's an account on Twitter that makes little cartoons about science, and they worked in collaboration with the Royal Chemistry Society making little cartoons that represented the posters. They were cartoon abstracts is what they called them. Abstracts, like the little summary of your poster. And since I didn't have one, they commented on my post and said, well, we decided to make you a special comment cartoon, and it was a little person chasing after the Twitter bird saying, wait. And it was so cute, and I just felt like someone cared that I had missed it.
Yeah.
And so that was my happy thing of the week.
I was scrolling through and I saw you like share that thing. And then I saw that they had mentioned you in the description. It's like a legit account or whatever. And I was like, I've clearly missed some important context here. There's a person trying to chase a Twitter bird. I understood that much. But I was like, why is this happening in a seemingly chemistry setting? Like this is
Right.
like a lot of the stuff that Melissa tweets about is with chemistry people.
Mm-hmm.
And I was like, this seems unrelated.
It's not. So that was exciting. And then I messaged that person to tell them how happy they made me, the person who runs that account. And we had a great conversation. So I love Twitter. You can make all kinds of cool friends on Twitter and academic Twitter. I've made connections that I never would have made in real life. So I think Twitter is a really fun place to do networking and meet science people. And that was just a small bright spot. So
Yeah, that's cool. That's funny.
So thanks, Errant Science, for making my week better. That was awesome. Love you. Go check out at Errant Science on Twitter. And thanks, Jim, for listening. And to you guys, the listeners, for coming and learning about why the sky is blue.
Anytime from me, and then also anytime from me and all the listeners.
Oh, thanks.
We talked and we were like, yeah, you know what? Anytime. Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chem4yourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Hefner and V. Garza, who reviewed this episode.